Hello everybody, my name is Alexis Prévost and today I will speak about critical exponents for a percolation model on transient graph, which is joint work with Alexander Drevitz and Pierre-François Rodriguez. So let me first define the percolation models that we are interested in this talk. The main object of interest will be the Gaussian phi field on the graph G, which will from now on be assumed to be transient and infinite. So the Gaussian phi field is just a centered Gaussian field whose covariance is given by the green function. So what I mean by that is that if you fix a vertex x, then you have a random variable phi x, which is centered Gaussian, and the covariance between phi x and phi y is just a green function between x and y. That is, if you start a random walk at x and let it run to infinity, how much time did you spend in average in a while? And associated to this Gaussian phi field, we can define a percolation model as follows. So for each edge between two neighbor vertices x and y, you can declare this edge open with a certain probability which is given by this formula. So let's say, for instance, that this one is open, which on the drawing is represented by a red edge. Then what this means is that since the plus here means the positive part of phi x minus h, if phi x is smaller than h, then this is equal to 0, and so this probability here is equal to 0. So the edge here, if it is open, it means that almost surely phi x must be larger than h, and phi y must also be larger than h. And if one of them is smaller than h, then the edge cannot be open. Okay, so you do that now independently for each edge, and you obtain a certain number of open edges in red and a certain number of closed edges in black. And you can then define a cluster of open edges by first fixing from now on some vertex x0 of my graph, and then kh is just all the edges which are linked to x0 by a path of open edges. And to this percolation model, one can associate, as usual, a critical parameter h star, which is as follows. If h is smaller than h star, then my cluster kh can be unbounded with positive probability, whereas if h is larger than h star, then kh is almost surely bounded. Okay, so you might wonder, why are we interested in this percolation model with a random probability for an edge to be open depending on the Gaussian phi field, which seems way more complicated than just looking at normal Bernoulli percolation? And the reason is that it is often actually easier to study than Bernoulli percolation. So the first instance of this was obtained by Brickman, Lebowitz, and Mice in one direction in 1987, and by Lupu in the other direction in 2016. And what they prove is that on ZD, in all transient dimension, actually the critical parameter h star is equal to 0. Moreover, there is no percolation at the critical point, h is equal to 0. And so this is something that is not known for simple Bernoulli percolation in low dimension. And moreover, we don't know an explicit formula, and we don't expect that there is an explicit formula for the critical parameter. So there seems to be something about this model which makes it easier to study. And what I want to explain now is that it is indeed easier to study, and in particular, one can find the critical exponents associated to this model. So the critical exponent of a percolation model are just numbers which quantify the size of the cluster kh at criticality or near criticality. So for instance, you have a number which will describe the diameter of your cluster at criticality, or the volume, or near criticality. So in order to study those, let me first introduce the notion of electrostatic capacity of a set K that I will denote by cap of K. And you can see it as a way to measure the size of K. So typically the capacity of K will be something that sits between the diameter of your set and the volume of your set. And this way of measuring the size of the set K is particularly well adapted to our percolation model because we have the following strong result. The density of the capacity of the cluster at some level H is known explicitly by the following formula, where here C and C prime are just explicit constants that I didn't write. So we know exactly the law of the capacity of my cluster, which gives us good information on how big exactly is KH. And let me give two applications of this formula, which are interesting in terms of critical exponents. The first one is about the percolation function. So let's look at the probability at a negative level that my cluster is unbounded. We know that this probability is positive, but actually by integrating this formula above, we are able to get an explicit formula, and this probability should be equal to the probability that phi x0 is between minus h and h. And what's interesting about this explicit formula is that as h goes to 0, where 0 is here the critical point, this decays linearly in h. So in terms of critical exponent, this means that beta equal to 1, because usually we say that the percolation function should decay to 0 as h to the power beta. So here beta is equal to 1. So another application is just to integrate this density between n and infinity at the critical point. So if I look at the probability that the capacity at level 0 is larger than n, what I observe is that this decays to 0 as n to the minus a half. So this is one way to describe the size of the cluster at criticality, but this is not the usual way of describing this size. So one usual way to do it is just to consider instead the radius of my cluster at criticality. And on Z3, so on the three-dimensional lattice, it turns out that the capacity and the radius are almost equal to one another up to logarithmic corrections. And so one directly infers that the probability that the radius is larger than n is of the order n to the minus a half up to logarithmic corrections. And so in terms of critical exponent, this means that rho is equal to 2, where rho is the inverse of the power which should appear in this probability. So now we see that we have two critical exponents, beta and rho. And actually, we expect that all the critical exponents are related by scaling and hyperscaling relation in physics. So these are relations that relate all the different critical exponents that describe in various ways the size of the cluster at criticality and near criticality. And if we believe that this relation holds, then these two exponents are enough to deduce all the other usual critical exponents. That is, for instance, on Z3, we have the following table. So this is a conjecture at this point, because we do not know if indeed these relations hold. But this conjecture makes sense, because independently, Lupu in 2016 proves that indeed eta was equal to 0. And using different methods, we are able to prove that nu is equal to 2 and gamma is equal to 4. So actually, this table should be true, and the only open question now is to prove that indeed alpha is minus 4 and small and large delta are both equal to 5, which are exponents which describe the volume of the cluster. So there are two comments to be made about this table. The first one is that we don't know exactly what these exponents are for independent Bernoulli percolation, but numerical simulation indicate that they shouldn't take the same values at all as the values in this table. So this is a different class of percolation than independent percolation. And this is due to the long-range correlation in the Gaussian phi field that appears in the randomness of our percolation model. So this Gaussian phi field has correlation between edges diverging to infinity, which decays polynomially fast. And what we believe is that if you take another percolation model with correlation which has the same decay as the Gaussian phi field in dimension 3, then this table of exponent should be the same for this model. So this is a new universality class for percolation model with strong long-range correlation. Okay, so if you want to know more about the topic, I put here some more references, and I thank you for your attention.